All right. Not much to announce. I think just for the tutorial, I'll keep you guys posted about what we should do for this coming Friday. I'm still debating what we should do. But I think for the graph, we definitely want to continue with the lecture today. We're going to cover more terminology. I think today will be slightly more challenging. So last time we only talked about vertices, edges, they're kind of simple but require stuff. Today we'll talk more about the different kinds of graph you might get into. So there'll be quite many terms we have to go over, just about basic terminology for today. And then next week, we got 2 more lectures before the reading week. So what I plan to do is we should do at least one traversal, like a depth first search in the class. And then we should also talk about how you can implement a graph in Java. We're going to talk about at least 1 or 2 strategies. So that should be enough, maybe for the coverage of your very first test after the reading week. So that will be the plan. I'll keep you posted about things. All right, if no question, why don't we do a very quick recap from last time, okay? So from last time, we actually started introducing about the idea of a graph, okay? So graph is really the most general form of data structure you can have. It's definitely more general than tree. There's so many things that you can do with a graph, but you don't necessarily will be able to do that in the tree, right? That's something we'll see maybe a little bit later. So graph for definition, you just got to remember you got a set of vertices and also you got a set of edges. So vertices and edges. Later on, when we talk about traversal, for example, or any algorithm on the graph, usually in terms of the complexity, like a running time complexity, what you're really used to back in 2101 is big of n. And n is usually the number of nodes in the linked list or number of elements in the input array. That's n. But in the case of graph, you will have to get used to, sometimes the complexity could be either the size of the vertices or the size of the edges or a combination of both. That's something you want to get used to. Right? We'll see some example very soon once we start talking about traversal. So just remember, graph has 2 parts. One is about vertices, the other one is about edges. Okay. And then we talk about the edges being either directed or undirected. And usually when it's directed, that means you want to somehow specify some kind of dependency, flow, or order. I think having directed graph is actually very, very useful. So that's something we also see. Certain algorithm that we're going to talk about definitely assume you actually got some directions on the graph. Okay, we'll get there a little bit later. And we kind of went through several examples over here, but you can definitely feel free to explore more examples yourself. There are certainly many things you can implement using either directed or undirected. Of course, you got to make that design decision before you even start with your application implementation. All right, we talk about 2 edges. One is about self-edge, and also the other one is about parallel or multiple edges. So when you actually got these 2 components, that simply means you don't really have a simple graph, right? A simple graph, by definition, simply means a graph without these 2 things. You don't have a self loop, and also you don't have the multiple edges or parallel edges. You don't have these 2, all right? And notice the word simple over here, right? So last time we only saw simple graph. Today we'll see something called simple path and also something called simple cycle. So there are so many terms we're going to see, in the very first 2 lectures for the graph. So definitely during the reading week, you want to maybe somehow make yourself like table, maybe flashcard, whatever, that's going to help you. Of course, you got to memorize some definition for sure to learn the graph. But, I try to keep the definition the minimum possible. These are the must know for you, really. All right, so we'll get to more terms today. All right, simple graph and also not simple graph. And we talk about degree of the vertices. Degree is simply defined by how many edges you really have that are incidents on the particular vertex, right? In the case where you have undirected graph, in that case, you simply calculate how many edges are incidents on the vertex. In the case where the graph is directed, then we kind of distinguish between in degree and out degree. In degree simply means the number of incoming edges. Let's say for A here, there's only 1 incoming edge. So the degree in degree is 1. On the other hand, for A here, you also got 2 outgoing edges. So the out degree is 2, right? So that's a simple notion. Also, we did some example together. You can also make up your own example as well. All right, and then we spoke about properties, right? So we're going to see lots of properties on the graph. Sometimes we have to make certain assumptions about the graph that we're talking about, so you can derive some useful property. So the one we were talking about is we assume there is no self-edge or multiple edges. So just simple graph and also undirected. However, these two, especially the simple part over here, is not a very necessary restriction. So if you look at the slides, I did put like an exercise for you. If we somehow relax the assumption about the graph being simple, which means you got to consider both the self-edges and also parallel edges, are you also able to prove the property? All right, that's something we can talk about as well. I can give you some hints, maybe a little bit later. Okay, so what we did was for each property, I would say every time we present a property, or if you somehow got yourself exposed into another property which we don't get a chance to talk about in the class, you always want to somehow verify the property itself on some example graph yourself, just to make sure at least the property makes sense. At least you know roughly what the property is about, right? That's basically what we do. So we use the same graph over here and to calculate the degree and to make sure it's 2 times the number of edges, right? So we can verify that the property makes sense for this particular graph only. We can only say that. But to really show that this property here works on every undirected simple graph, we have to use some formal proof. And we're going to see some proof technique called mathematical induction, very, very common. Very, very often. So we're going to complete this proof. I'll recap what we have done last time. We're basically almost to the last step for this mathematical induction. I'll talk about it, just bear with me. So we're going to finish this one here today in the beginning, and then we'll see another property again where we can use mathematical induction. There's so many properties you can just use mathematical induction. So we're going to do so many examples in the class. Of course, do expect you might get some similar question in the test or exam. Right? Just make sure you understand the 3 steps about mathematical induction and how you can do that. I would say typically for the very two steps about showing the base cases and also stating the inductive hypothesis, these 2 are rather routine because once you're given the property to prove, you can already know what's the inductive hypothesis really. The key step is really about 3rd step. Over here. That one is going to be very creative step you have to come up with, just like doing a math proof. But I'll just do example to give you more intuition. I'll get to this one a little bit later. And then we spoke about another 2 properties. So this one here, since we talk about directed graph, so we'll distinguish between in degree and also out degree. So we're saying that if you got a directed graph, the sum of the in degree will be the same as the sum of the out degree. And we use a table here to show that this property holds on this particular graph, right? But to really prove it, again, you can use mathematical induction. So that will be some exercise for you, right? So we're only going to do one mathematical induction on this property here. For the other 2, this one here, about in degree and out degree. Another one, which is about how dense your graph is, about number of edges upper bounded by the big O of n squared, which is about the vertices, right? So that's something you also want to try using mathematical induction. The first 2 steps will be very routine. You just want to state the base case and also inductive hypothesis, but the 3rd step is going to be more creative. That's something you're going to try, okay? All right, so this one here, just talk about the number of edges will be less than or equal to. When it is exactly equal to this number over here, right? So we talk about the intuition behind this one. That means from every vertex, okay, let me show this. From every vertex, you can simply go to every others, okay? We call that a complete graph, okay? So that's somewhere I mentioned, okay? The graph is complete, right? Okay, so we talk about simple graph, we talk about complete graph, right? From last time. We're gonna see more terms today. Okay, guys, any question from last time? All good? Okay, we just see more terms today. But before that, let's complete that mathematical induction. Okay. So this is what we had from last time, right? We only got the 3rd step unfinished. Let's now do that, right? But before that, let's review what's really required for mathematical induction. So mathematical induction is going to be some induction on certain things. In this case, we'll say on the size of the number of vertices. So in this case, we're going to start with some, also we'll make some additional assumption, non-empty. So that means the minimum size for the vertices will be just 1. In that case, you only got one single vertex in the graph, only one. In which case, you have no edges, right? In that case, edges will just be 0. So the degree will just be 0. And the math will just work out for the base cases. Usually, base cases will take very little work to really show it, right? So base case is good. What about the inductive hypothesis? So here for inductive hypothesis, we assume that given some graph, you got a set of vertices V, capital V. And then when you sum up the degree for every little v, which is a member of the capital V, the number will just be 2 times the number of edges, right? And here we're saying that the number of vertices is simply some k value. And k just got to be big enough, just bigger than the base case. So that's why we say strictly larger than 1. So you can say over here, basically we are moving away from base cases. So that means it's more substantial than base cases. More substantial than base cases. Right? That's important, right? It's really important to say how large k is. And step number 3. We somehow want to extend. So think about this is the inductive hypothesis. We assume we have k vertices. And also we got n edges. Okay, that's what we assume. Okay, so you can think about here, the k here is really the number of vertices. And the m here is really the number of edges, right? We just use different symbols to represent them, all right? And based on the inductive hypothesis that we assume, right? Inductive hypothesis, right? We can assume this particular property, okay? So let me write it down. So this one here, based on the inductive hypothesis, we know that the sigma of V, capital V, and the degree of V will just be 2 times n. Okay, n right here. And we're going to use that inductive hypothesis. What is really so important for step number 3 is somehow you want to show that the property still holds when you try to extend something that's larger than the inductive hypothesis. To really show the third step, you also have to use the inductive hypothesis itself. It's a bit like a calling a recursion. You're making some recursive call. At the same time, you want to do a little bit additional stuff at the same time. Okay, that's more like an analogy. All right, let's see how we can do it. The idea would be we want to make a strictly larger graph. You can see we assume a graph with k vertices. But now we're just going to make it k plus 1, strictly larger, okay? By adding 1 vertex. So the vertex we're adding is called y, right here. Okay? I'm going to redraw this diagram here and see how we can make it happen. Actually, we can use the diagram just right there. Okay? So now the question is, if we have a graph like this, that's what we have. We want to add 1 more vertex right here. What would be the way to really connect this y over here such that it will remain to be a simple graph? All right, so that's really the idea. Okay, I'll put it here. You want to ask yourself the question, what are the possible ways to connect y to the existing graph? And the result should still be a simple graph. That would mean when we actually want to connect y, we cannot use self-loop. We also cannot use parallel edges. These are the 2 things we cannot use. Other than that, we can use anything. Well, basically just use some edge. Okay? So this part is actually very important, right? So that's also something you want to include in the proof. So what are the possible ways to connect y to the existing graph, right? We know that you cannot use parallel edge. So self-edge, no, you cannot do it. Also for parallel edge, you also cannot have it. So these are the 2 things you cannot do to really connect. Okay? So let's not worry about simply have 2 things that are not that's kind of disconnected. Let's not worry about it just yet. Okay. So one way to do it for sure would be, let's say there is one. So now you got to think a little bit more abstractly. Let's say we have a vertex right here, right? One of the k vertices. What would be the way to connect these 2? Well, as simple as connect like that. That's one way, right? I can also choose another vertex over here and then also connect this way. This will also remain to be a simple graph. Agree so far? All right? So now, how many vertices can I choose up to connect to y? How many? K, exactly, right? It could be I choose 1, I can choose 2, I can choose up to k. So I got k possibilities. All right? Either one of them, either one of the k solutions is going to make it happen. Okay? So now we're going to make this general. Okay? So now we're going to say this. Okay, let me just write this one here. So here we can choose up to k vertices to connect. Okay, let me write it down as well in the third step. Okay, so now we'll say choose. So how many do we choose? We can choose up to k, right? So let's say let's create another variable called d, standing for degree. Let's say we choose d existing vertices and connect them to y. So think about how many do we have over here. It can be up to d, where d is less than or equal to k. Right? This inequality here is very important. We are not committing to whether it's going to be 1 or 2 or 3 or 4. It can be up to k. Right? And let me just put that side condition here. Okay? So d will be less than or equal to k. Okay? That's so important. So now we can use the d to manipulate the formula and get our final answer. Okay? Okay, hopefully so far so good, right? So so what I'm really trying to extend from Monday was we choose this, we have this new vertex y, and there are many different ways to really connect this y to the existing graph. There are up to k different ways, right? But each one of them is simply gonna draw a single edge, and then, right, from there. All right, let's now try to write out what's gonna happen here. Okay, let's now write some equation here. So I'll start from this. First of all, I'll start from the sigma. I'm going to calculate the sum of the degrees for all the vertices in the new graph, which will be all the vertices over here and plus this new vertex. So that'll be the new degree number I want to get, right? So I'm going to say this. Little v, a member of capital V. You can think about capital V is from the existing graph. That one there is union with another new node, which is y. Right? You can see I'm writing this explicitly. Little v can be chosen from either here or maybe the y. So I'm covering exactly k minus 1 vertices. But if you like, I can also write it down. So this part here tells you that we got k plus 1 vertices. And then we're going to sum up the degree of little v. All right, let's see what it is. It turns out it's very simple math, okay? So first of all, let's apply the inductive hypothesis. Inductive hypothesis tells us the sum of all the degrees in just this part when we exclude y. Sorry. Just this part excluding y. How many do we have? 2 times m. Agree? Okay? So I'm just going to write out 2 times m. And let me make some annotation for you right away. You can think about this as inductive hypothesis, excluding y. Okay? It is so important in the third step, you must use the inductive hypothesis somehow. Now, we want to plus some additional ones. This is a critical part. Now, I'll pause a little bit. What should I add? So the additional part that remains to be written are the additional degrees I'm introducing by having y, and also making exactly d edges to connect to y. Exactly how many more degrees am I adding? I'll give you one more hint, okay? Let's say, for example, let's make, again, somehow you're not exactly sure about general case, make some concrete case. Let me say that, and I'll take your answer, okay? Let's say this. Let's say between y and the existing graph, I'm only adding this. I'm only connecting these two. How many degrees am I adding? 2? Why 2?
Because there's a degree for y and a degree for the...
This is no, right? Let's say this is x. So I'm gonna add 1 degree for x and 1 degree for y. Agree? So that means over here, I'm having d different edges. That should be d plus d. All right? That should be d plus d. So think about the d over here are the degrees from, so these are from existing nodes to y. And the d over here will be from y to existing node, bidirectional, basically. From y to the existing node. All right. It is important for you to see why that d should be counted twice. Right? Again, for any edge I'm introducing, I'm basically having two ends to be counted as degree. Right? Got it counted twice. All right. Okay. I'm just going to simplify the number, and then we should be almost there. Okay. So let me put a star here. So that number there will be 2 times m plus d. All right. What's m plus d? M plus d is really the number of edges in the new graph, because I'm introducing d edges in total, plus the existing m edges. That's really the number of edges in the new graph, right? So this one here is really the number of edges in the extended graph. Okay, so what we have already proved it. Okay, so now the big picture is we start with this one here. Left hand side, it is equal to 2 times the number of edges. Just that the number of edges in the new graph is m plus d rather than just m. And somehow to really show that we got this one here, we have to use the inductive hypothesis. All right, so that's why. All right, so that's the proof. Okay. I would say this one here is very nice because it really kind of require you to think abstractly about having some cloud, which would be something that's kind of specified by the inductive hypothesis. And think about how we can extend this cloud over here just by one single vertex and everything else. Right? Guys, any question about this? Any part that's not clear exactly? Okay? Okay. We're going to see more example like this, right? We definitely got lots of chances to practice, but it is very, very important to see how things should be understood at the abstract level. Okay? Okay, if that's good, let's now move on. Okay? So today we're going to start introducing more terms. Okay, let's see how far we can go. All right, the first 2 terms about path and cycles. Okay, so that's the first one. Okay, let's now do some pages together. Okay, so that's the graph I'm going to use as an example right here. Okay, let's talk about different definition. Okay, what is a path? According to the definition, a path is simply alternating vertices and edges. You start with some vertex and then go with some edge to the destination vertex and etc. Okay, so that's the definition for a path. So let's start with the path, and we'll see some example right away. Okay, the path over here, so it's alternating vertices and edges. Let's see one example. Okay, the one that's on the slides would be like this. So one example path. It's going to be, let's say, usually we just use a parenthesis, just say it's a sequence, right? Or we can use an angle bracket, doesn't really matter. So we always start with a vertex, the starting one. So let's say we say F, and then H, S, and also vertex D, and then HT, and then vertex E, HP, and vertex F, HN, and vertex B. So this is the starting vertex. Of the path. And this will be the end vertex of the path. Okay? What is this sequence exactly saying? Right? Let's now do some annotation, highlights. So this one here is basically specifying I go from F and then I go for S. And then I go to D and then I go to T. And then I go to E, and then I go to P, right? And then I go to F. You can see F appearing twice, by the way, right? Which is okay for a path. You can see F appear twice. And after F, I go for N, and then I go to B. It's a path, right? Like that. This. It's a path. All right. A path does not need to cover all the vertices in the graph, just a path, right? A path can be as simple as maybe just from a single edge. For example, if you simply go from D, S, F, that's also a path. That's the simplest one. Okay, okay, that's about a path. And then about cycle. What's a cycle? First of all, a cycle is a path. And then a cycle is a path where you can see the same vertex appearing more than once. Actually, the path we just saw, it is a cycle. You can see this one here is a path. At the same time, you can see F appearing twice. How do we see that visually, right? As long as you have some loop like this, then you have a cycle. Okay? You can see F over here appearing twice. We start with F, and somehow we go back to F itself, so we have a loop. As soon as you have a cycle in the path, that means the graph itself is no longer, well, I'll get to the term a little bit later. Let me get to that right now. Graph with a cycle. We say that a graph is cyclic. Okay, it's an adjective. And also a graph with no cycle is called acyclic. A graph without a cycle. It is something called acyclic. Okay, just notice the term. Cyclic versus acyclic. Okay. Okay, let's see another cycle. You will see another example in the slides actually, but that one there you can definitely feel free to actually see what it really corresponds to. So you will see that on slide number 17, right? You can see the example here. So we already went through this path over here. You can also take a look at the cycle over here. And this one here, just another example, right? Where you will see some loop there. Okay. Let me just talk about the next one. So this one here is path and cycle at the same time. Also a cycle. Okay. So we're done with the path, we're done with the cycle. Okay. Let's talk about simple path and simple cycle. What does it really mean? Simple, right? Simple path, according to the definition, okay, let's again look at the definition on the slides. A simple path is simply a path with distinct vertices. It's basically a path without any cycle. Okay. Simple path is basically a path without any cycle. Right? Let's just take one example. So if I say simple path, similar to this one here, let's say I can simply go for FDE rather than going back. I can say FDE and then A. How about that? It's a simple path, right? So that one there, I can say F S D T E O and A. Always remember, you got to start with the vertex and end with a vertex. So that one there goes like this. So you go from F, go to S, go to D, and then go to T, and then go for E, and go here, and then end with A. Right? You can see this one here. From here, there's no cycle. It's a simple path. Okay. What about a simple cycle? That's kind of interesting term, a simple cycle. Okay. You definitely cannot say a simple cycle is going to be a path with all the distinct vertices, because in that way there's no cycle, right? So you basically want to say, except for those two vertices that will make a cycle, apart from that, the rest should be a simple path. That's the right way to put it. I'll put it down. Let's first of all see the definition right here. Sorry, keep going the wrong way. A simple cycle, right? A simple cycle here is still a cycle, except we're going to somehow look at anything else other than the vertices forming the cycle. From that, there should be no repetition of the vertices. Let's see one example right away. Okay. Simple cycle. This might be the trickiest one to really get right. Okay. So if you look at a simple cycle, so the way to understand it is, number one, it is a cycle. For sure. You gotta have that, that kind of repeating vertex, but only for two occurrences, only two, right? So basically, except the two vertices forming the cycle. All remaining vertices are distinct, no repetition. And we'll see one example. All remaining vertices are distinct. Okay, so all the remaining vertices are distinct. Okay, one example here. How about a simple cycle? So simple cycle. Okay, the one on the slide, let me just copy the one on the slide and then let's see why it's a simple cycle. Let's say I start with E. And then I go for T, and then I go for D, and then I go for R, and then I go for C, and then Q, and then A, and then O, and then with E right here. Number one is a cycle, because I have E here and E here. So the fact that I got repeating vertices is a cycle. So this tells me that it's a cycle. Everything else, no cycle. Everything else, if you look at just this part, for example, right? Or more specifically, just for this part, you can see there's no repetition. We only got D, C, and A. So this one here is a simple path. Without any cycle. Let's try to visualize this particular example here. Okay, if you look at that one there, so we got, we start with E, and then let me just copy that one again, shall we? Let me just copy that one again. Okay. Just take that example. Right here. I'll make it smaller. Okay, right here. Okay, so for this one here, we start with E. We start with E, and then we go for T, and then we go for D, and then we go for R, and we go for C, and we go for Q, and then we go for A, and we go for O, and we go for E, right? The orange one itself is definitely a cycle, but it's a simple cycle simply because if you only look at the sub part of it, like at this part here, if you look at only this part here, starting from starting from D here, and then this part here, this part here, this part here, and this part here, without worrying about the two vertices over here that forms the cycle. So just the purple part here, this one here is a simple path. All right, any question? Anything that's not clear? So what you want to understand is somehow the simple cycle here contains two things. One is it contains a cycle, and the rest will be perceived as a simple path without a cycle. If you can do that decomposition, it's a simple cycle. If you cannot, then it's a not simple cycle, basically. Okay. All right. Let's now talk about two more things. Another two things about reachable versus reachable path. That one there is actually much more intuitive. What about reachable? Reachable by definition. Okay. So we say we got two vertices in a graph. If one vertex is reachable from another vertex, that means this one path that's defined by the graph. You can go from one vertex to another, right? Path. Of course, the path over here doesn't need to be shortest, right? We'll get to the shortest path a little bit later, okay? Reachable is very easy to visualize, okay? So for example, if you want to say, is it reachable from A to F? It is, right? For example, you can go this way. That's a path. Is it reachable to go from A to B? For sure, that's a path, right? In this particular graph, between any two vertices, there is a path, at least. So we also said this path, this graph here is connected, but that's something we'll get to a little bit later, right? All right, so reachable is easy, and also reachable path is, if you say two nodes are reachable and show me the reachable path. In this case, it will be A, O, E, P, and F. That's a reachable path, okay? So whenever you say it's reachable, then of course you will be able to give a reachable path. Okay. Right, so we talk about path, cycle, simple cycle, reachable, and reachable path, right? So these are important terms. And reachable here is also a very important problem we're going to solve later, right? A simple problem could be, let's say given a graph. You want to know whether or not there exists a path between any two arbitrary input nodes. Is there a path? If there's a path, return that path. If there's not such a path, then you're going to say false, for example. Right? It's a reachability kind of problem that we're going to solve later. Okay, so reachable here, let me just say one more thing, and then we'll move on to the next term. So reachable here, the reachability problem. Given G with vertices and edges is V1 reachable from V2. And of course, V1 and V2, they are both from V. V1 is a member of V, V2 is a member of V. Is it reachable from one vertex to another? If it is reachable, give me the path. We should be able to calculate this automatically. We're going to do some graph traversal, which I'll start doing on Monday. Okay. All right. Guys, any questions? Right? Good. All right, why don't we take a very short break? I still got, well, I think these are the foundation, and then after the break, we're going to talk about different kinds of graph, right? Then we can introduce more terms. Okay, why don't we take a short break? And you can, all right, so before the break, we spoke about path and also cycles. And we're going to talk about a series of terminology about different kinds of graph, right? Let me just give you a very quick bullet point about the list of things we're going to talk about. We may not be able to finish everything today. We'll try as much as we can. But just before that, I can just tell you what we're going to talk about so you can have some idea in your mind, okay? We're going to talk about the following, okay? We're going to talk about something called subgraph. And then we're going to talk about something called spanning subgraph. So these are the two things we're going to talk about first. And then we got something called connected graph. Or connected subgraph is okay too. All right, so these are the three we're going to talk about first. And then we're going to go into something called forest. And if you got forest, it also makes sense to talk about something called tree. All right. And the tree over here is not, you can think about the tree here is really similar to what we talked about back in 2101. But I would say not try to compare every one correspondent. You don't need to, right? Tree is just like a special case for a graph. Okay. So forest and tree. And then we got spanning tree as well. Right, so these are all the terms that we have to go through in the basic terminology, right? So we're going to talk about each one of them and give some example and give some definition. And whenever we can do a little bit of exercise to really strengthen your understanding, I'll try as well. But I think ultimately we should also draw a table to really see how to compare each one of them. We'll do that together, right? I think it's okay. Also can help you when you review the stuff, right? Okay, we'll talk about it. Let's now start with the first one, subgraph and spanning subgraph. Let's start with that first. Okay, so let's first of all start with a subgraph, and we'll first go over definition as well. Okay, first of all, subgraph. Okay, given a graph with the vertices and edges. Okay, what's a subgraph? Okay, so you got to use some set notation here, but it's a very basic one, right? So a subgraph is just another graph. And then what's really important here is we should really get the vertices in the new subgraph should be a subset of V. Subset here means that it might contain only a portion of the vertices, or it might contain every vertex from there, right? It's what a subset is really saying. And also we also contain some edges from there as well. Let's see some example right away, all right? So we focus on subgraph for now. What's the simplest subgraph? Could be empty, actually, right? Remember subgraph over here? Okay, let me start with the simplest one, right? You can see the definition. So if I have a subgraph, by definition, subgraph G prime, okay? Which will be V prime and also E prime, right? I use the prime just to say they're different sets. In order to be a subgraph, V prime is a subset of V. And this is V right here. Think about this is G, which will be V and E. So this is like a graph I'm using as a reference. I want to create some subgraph from there, right? So for this graph here, I got a V, which will be A, B, C, D, E, F. That's a V. What about the E? It will be N, N, O, P, Q, R, S, T. Right? So that's a reference graph I'm starting with. Now I'm asking about what can be the subgraph from this particular graph G. Right? Let's talk about the simplest one by definition. And also E prime is also a subset of E. Subgraph number one. G prime, 1. Empty graph. Where the V prime is simply empty. And the E prime is also equal to empty, just nothing. Sounds very funny, but it's actually okay mathematically because we say subset. Empty set is always a subset of any set. That's a very simple fact we learn. Right? So empty graph is always a subgraph of any graph. Let's start with that. Or we can also have, let's say, G2 prime, a graph with a single node without any edges. Like a one vertex or one noded graph. For example, you may have, let's say V will be, let's say I only got A. And E prime will just be empty, right? Corresponding to just A. That's it. No edges, just single node. May not be very useful, but again, it's a subgraph, right? You might be asking, can we have a subgraph that contains only one edge? No, you cannot, because by definition, edge should be connecting two vertices, right? So that's also important for me to write down. Number 3, a subgraph cannot contain just a single edge. Okay, that's important, right? You can have a one-noded graph, but you cannot have a one-edged graph. You cannot, by definition, all right? All right, so these are the simplest one. And let me give you another example, right? Let's say I can have a subgraph. Let's say visually, let's say that's a subgraph I want to have. Let's say I want to have the B here, A here, and also C here. So these nodes I want to include in my subgraph. And then I want to include vertices, edges, this one here, for example, right? I cannot really include just an edge like this without including E, right? You know that, right? Okay, just make sure you see the point. Okay, another example here. So maybe G3 prime, which will be, for example, we got A, B, and C. A, B, and C. And also for the edges, I got M and Q. Okay, one more. The smallest subgraph is simply just empty, smallest one. What would be the biggest subgraph? The same graph, yeah? A graph is also a subgraph of itself by definition. Because we have, again, we got subset relation, right? It can be exactly the same, okay? All right, let me put that as well, okay? Example number 5. So G can be its own subgraph as well. So think about here, this will be the maximum subgraph. Maximum subgraph. And this one here will be the minimum subgraph. So the notion about subgraph is very powerful. Basically, you can just choose some collection of vertices, as many as you like, and have some edges connecting between them, right? All right, I would suggest I move to a new page just for spanning subgraph, which will take another set of explanation. Okay, so let me just go to another page. Right here. Okay, let's talk about spanning subgraph. The easiest way to remember the definition is basically a subgraph that spans. A subgraph for sure that spans through all vertices. What does that mean? Okay, so you can think about when we talk about subgraph, we say that the vertices only need to be a subset. In the special case where we got an equal, v prime is exactly equal to v. It's a spanning subgraph. All right, I'll put it down. Okay. So here, according to this definition here, we say G prime, and then let's say G prime will be V prime and also E prime is a spanning graph, spanning subgraph of G if and only if, all right, let's make it a little bit more precise. V prime is exactly equal to the V. And the edges would still be a subset. Doesn't need to be exactly E. Doesn't need to be. Okay, so what you want to notice is this relation here, equal. All right? And let's now try to see some example here. Spanning subgraph. Oh, by the way, this is a subgraph, right? Is it a spanning subgraph? No, because this subgraph here did not contain 1, 2, and 3. Right? It's not a spanning subgraph. Okay? So you can think about this one here. A subgraph but not spanning. But not spanning. All right? How can we make that spanning, for example, right? To start with, we know that for sure all the vertices must be included. So we must include all the vertices. And this already is a spanning subgraph, even though we have no edges. Okay. So let's say number 1, we have G prime. 1 will be, let's say, we got A, B, C, D, E, F. And we have no edges. This is by definition a spanning graph. That simply means we got all the nodes disconnected from each other. That's okay. Because the edges over here, empty set, by definition, is a subset of the set of edges. And this one here, A, B, C, D, E, F, is exactly equal to the reference graph vertices. It satisfies the definition. Okay? So think about this part here is exactly equal to the V. And this one here is a subset of E. Right? So this will be kind of the smallest subgraph that's spanning you can have. Right? And of course, from there, you can add as many edges as you like, since you got all the vertices. Is it okay that we have a spanning graph over here? Somehow, there's no reachable path between the nodes. It's okay. Spanning is a concept you want to distinguish between connection. This is different, right? We talk about only about spanning. We will just talk about covering the vertices. Okay, let's see one more example. So here we can get number 2. G2 prime. So we still need to have all the A, B, C, D, E, F. And we can add more edges. Let's say I want to add maybe, let's say 3 edges. Let's say M, O, and P. Right? In that way, I'm basically adding M, O, and also P. Right, so I got 3 edges over here. It's still a subset of the E. And this part here is exactly equal to V. Okay? It is about spanning subgraph, just talking about vertices. And it is so important, I'll write it down here, but we'll make that distinction even more. Okay? Spanning is not the same as saying connected. Don't get confused. Okay? You might be thinking, oh, there's no reachable path between, for example, between B and, let's say, there's no reachable path between B and C, but it doesn't really matter, right? It's something about connectivity, which is another concept. Okay. All right. The next one. Before I get to the next one, I believe I have some little exercise for us, right? This one here is pretty much already set, but I can just let you just pause for a moment to think about. So let's say we're having a subgraph right here. And we know that subgraph here, V prime is a subset of V. E prime here is a subset of E. It's a subgraph. How can we formulate the condition for a subgraph, but the graph there is not spanning? What will be the condition? We know that in order for that to be spanning, the V prime here must be exactly equal to V, right? But now I want to say something that's not spanning. What will be the right operator to use?
Proper subset.
Ah, good. Okay, that's easy, right? Okay, that's good. So the way to visualize this is something I want to show to you as well. Okay, so let's say we got a spanning graph. So think about this set here is all the spanning subgraph. Of G. And then you get a strictly larger set. Right here. It will be the subgraph of G. And we're basically talking about if I want to choose a witness just from here, that is a subgraph, but it's not spanning. That would mean this must be a G prime, and then V prime and E prime. And the condition would be such that V prime should be a proper subset, as you said correctly, of V. And the E prime over here will just be a subset. It's okay. Right, so the main thing for me to really show to you is really about this proper subset symbol. Okay? Proper subset simply means you just don't cover all the vertices. For example, you might just have, for example, cover B, A, E, C, and D. And then you might still have the rest of the edges covered. But it doesn't matter, since you don't have F. It's not spanning, right? Just one example. Yeah, think about it. All right, the next one. The next one, we can look at something called connection, okay, connected graph. But before that, let's look at some definition. Okay. So we talk about subgraph and also spanning subgraph. Let's talk about connected graph and connected components, right? So these are two things. Let's talk about connected graph here. What does it really mean for a graph to be connected? You'll be connected if there's a path between any two vertices of G. All right? So if you choose any arbitrary two vertices from the graph, there should be a path between them. All right? Okay, let's see this example here. So let's now take a look. If I have, for example, so let's now try to see if we can formulate this a little bit. Okay? Connected graph. Connected graph. So we say that, let's say connected graph, let's say G would be V and E. So we say connected G. If and only if, right? Let's think about how we can formulate it, right? We can use a universal quantification, and we can use two dummy variables. Each one of them is going to represent one vertex we can choose arbitrarily, okay? We can say for every U and V, both are vertices. You can say U is a member of V, and also, actually, I better not use U and V. How about just X and Y, okay? So, because you might sometimes get confused about the little v and capital V. X and Y. So X is in V, and also Y is in V. Okay? Given any two arbitrary vertices chosen from the graph, it should be the case that this part here we can say a little bit more informally. X is reachable from Y. X is reachable from Y. Okay. For example, is this particular graph connected? So you got to choose pairwise. For example, you choose A and B, there's a path. If you choose A and F, there is a path. If you choose A and E, there's a path, etc. Right? It is connected. You choose any arbitrary two vertices from the graph, there's always a path, always reachable. All right? So think about the connected is very closely related to about being reachable at the pairwise vertices in the graph. All right, any question about being connected? It's also quite straightforward, right? So now let's have a question for you, okay, to think about. If I say I have a spanning graph, can I say that spanning graph is guaranteed to be a connected graph?
No.
How come? Yeah, you're quite right. Yeah, exactly. So because spanning graph only cover all the vertices, but has nothing to do with the edges. Because we do need the edges to build a connection, but there's no requirements on that. Right? That's intuitively, right? Yeah, that's exactly right. Okay, spanning graph over here only require vertices to be covered. But no requirements, not require edges to build the necessary connection. All right, that's pretty much the hints I want to show to you. Okay, why don't we take a quick look on this? Okay, let's say we got a graph here. Okay, let's now just take a look at that. Okay, so let's say we have A, B, C, D, E, F. Okay, A, B, C, D, E, F. The fact that we already cover all the vertices guarantee is already a spanning graph, but it's simply not connected just yet, right? There's already a witness. But let's just build some vertices. So you can see N, P, S, T, R. N, P, S, T, R. This is definitely a spanning graph, but it's not a connected graph. How come? How would you justify it's not a connected graph? Which one? F and B? Yeah, for example, right? Yeah, you're going to show two vertices where there's not a path, right? Very good. Okay, this one here is a spanning graph. But not connected. Okay, for example, there's no reachable path. From B and F, for example, or from A and C. And a little bit look ahead, right? You can see somehow A and B are the maximum nodes we can actually build, we can actually cover by the reachable path, right? You can see we cannot really build any further, right? We cannot really grow this component any further. It's called a connected components, which we'll see the next, okay? At the same time, this part over here is really the maximum component that's connected. We cannot go any further, okay? Let me just make a note here. That's something we're going to see. So we say that this part over here is one connected components. This one here is just another connected components. Okay. This one here is the maximal connected component. There's just another maximum connected components. So these two somehow are in isolation by themselves. You can think about there are two islands without any bridges between, right? So there's also some algorithm we're going to see later. Given the graph, we may just want to ask how many connected components do we have in the graph? In this case, for example, if I give you this as an input graph, how many connected components? 2. 1 here and 1 here. All right, that's going to be another algorithm we can use. We can actually build. All right. All right, very good. Okay, let's now go a little bit more. Okay. The next one will be a connected component. Okay, this one is fun. Okay, let's go over some quick definition. Okay. Okay, let's see. Connected components. All right, so guys, this line here is very important. Whenever we talk about connected components, it will be the maximum connected subgraph you can find in a graph, right? So the correct way to say that, which I said a little bit not imprecise. Let me just change that a bit. Okay. Maximum connected subgraph. And maximum connected subgraph, another subgraph basically. Right? So this is one maximum connected subgraph. This is just another one. And whenever you say maximum connected subgraph, it's called a connected components. That's the right way to say that. And when you say maximum connected subgraph, it's called a connected components. Okay, I'll write it down separately. Okay. So whenever you see anything called connected component, of some graph G, you're really basically saying it's the A maximal connected subgraph of G. And the maximal over here is in the sense that you are not able to build any other, you are not able to expand it into another connected subgraph. No further extension is possible. No further extension is possible to make a larger connected subgraph. Okay, so that's really the insight, but if you look at this one again, bear with me. So this one here is definitely the maximum because you don't really have any more edges, right? Because according to the subgraph definition, you only got between A and B, right? You don't have any edges between A and C. You don't have it. So you cannot really grow the subgraph that's connected. All right. Let's now look at one exercise here. Once you see the graph visually, it's actually not difficult to see what's the connected components, right? Let's say for this one here. How many Connected components? 3. Quite obvious, right? Yeah, once you see that visually, it's not bad, right? So first one here is this one here. You can see these 4 nodes are really like an isolated island. You don't have any edge to go to connect to another connected component. So this one must be a connected component by itself. All right, that's number 1. And then you got number 2 over here. Okay, and finally, you got number 3. So basically, between each of the 2 connected components, there's simply no edge between them. Okay? So think about connected component 1. And then connected component number 2. And then connected component number 3. Okay, let me say one more thing here that's also very important. Okay? Between each pair of connected components. Let's say we got connected component 1 and connected component 2. What does that really mean? That means if you take some arbitrary vertex from CC1, take some arbitrary vertex from CC2, there's no reachable path between them. Okay? I'll write it down. So in this case, again, math, discrete math, will actually help to really formulate the meaning. So we say for every, choose some x from this, I'll visualize that. This is connected component 1. And this is connected component 2. I choose some arbitrary vertex from here called x. Choose another arbitrary vertex from here called y. And there's simply no reachable path. Doesn't matter which one I choose, right? It's going to be exhaustive combination. So for every x and y. And then we say that x is a vertex in CC1 and y is a vertex in CC2. It is the case x is not reachable from y. Right, so that's a formal predicate. Of course, a certain part we don't really say predicate, right? Just we can kind of use the operator to actually show the meaning more precisely. Okay, like that. Okay, good. All right, about connected components. Okay, questions? All good? Okay. I think we just got about forests and trees. Okay, we got forests and trees and also spanning tree. How about this? I would suggest we actually leave this discussion here to Monday, and then we got just 3 more turns to really introduce forest, trees, and also spanning trees. After that, we'll actually speak some property about the relationship between number of edges and number of vertices when we got different shapes of the graph. That's something we'll do as well, and then we'll show you another example about mathematical induction. That's something we'll do in the first half, maybe on Monday's class. And then in the second half, I would like to do depth first search about how you can do traversal on the graph. That's something we should plan to do on Monday. And then maybe on Wednesday, the last class before the reading week, we'll talk about how you can implement graph in Java. There'll be some implementation strategy we got to learn. All right? All right, thank you so much. And then I'll reach out to you about what's going to happen on Friday. Okay, thank you.